Okay, so last time we started discussion of the adjoint functors, and today we're going to continue. I'm not sure can we finish today, but I'll try to finish this topic today. So let me briefly recall what was the situation. We considered the situation we have two functors. I'm going to call them, say, f and g between categories C and D. So this is the data that we have, sorry, f and g, not another f. And we call them adjoint pair. So this was the notation, and in this situation f is called left adjoint, g is called right adjoint if there is a bijection natural in both variables. So from the d f of x. So this is, by the way, the reason why f is called left adjoint in the Holmes set. This is on the left. And g, of course, is on the right. So of course this is supposed to be the case for any x and y. Okay, so these are in different categories. So x lives in the category C, and y lives in the category D. So we call such functors adjoint. We look at the example of a free vector space. We're going to look at a lot more examples probably in 2 weeks, because next week we're going to have our first quiz. So, but in 2 weeks we were going to have seminar on most on adjoint functors. So, and this bijection that we have here is supposed to be natural. And last time I formulated this in terms of diagrams, and then I reformulated these neutrality conditions in terms of two identities, quite important. So, if we, for example, say that G is a map from the f of x to y, this is precisely notation from the previous lecture. So then, by definition, I call G bar to be the result of the application of the map phi to the G, and the same in the other direction. So kind of I'm using notation, using the same bar for the phi and phi inverse, but I think it's okay. I think it's easy to understand from the context which bar I'm using. So f now lives in the right-hand side of this bijection of two Holmes sets. So then f bar is by definition phi inverse of f. So, and with this notation, the neutrality conditions can be formulated as two formulas. So first formula is the composition of the h and g with the bar is the same as the g applied to h composition with the g bar. And the second formula is this one. So g and f as before. Okay, so the last observation that we've done was that we can introduce the two natural transformations called the unit and co-unit of the adjunction. So the standard notation is eta sub x for the component x, and that was by definition identity transformation on the object x with the bar. So we can think about this as a natural transformation from the identity functor to the composition of functors g and f. So that is the unit, and of course there is dual notion, the co-unit, which is by definition identity on the g of y with the bar, and we can think about this as the natural transformation from the composition of functors f and g to the identity transformation to the identity functor. And we notice that these two natural transformations satisfy two relations, which are called triangular identities. So let's say triangular identities, which can be written as the commutativity of two triangles. So this is the one, and there is another one with a G. Okay, so that was what we've done last time. Now the first goal of today's lecture is to show that this data, this bijection of two homosets phi, which is natural in both variables, is the same information, it's precisely the same data as these two natural transformations satisfying these two triangle identities. And the proof essentially follows from the following lemma, which is very simple and naive observation. So if we have pair of adjoint functors, so f is left adjoint to the g, so then I can compute g bar, which before was defined in terms of the map phi. I can compute this as the composition functor g applied to the map g, taking composition with the eta sub x. So of course this is for any g which is a map in the category D from the f of x to the y. And there is another formula for the f, so f bar can be computed as the composition of the epsilon sub y, composition with the functor f of the map, little f. And that is of course again true for any little f that is a map in the category C from the object x to the g of y. So what we can see here is that this essentially what the information we have in phi is just these two maps, how we can go from g to the g bar and how we can go from f to the f bar. And this information can be recovered if I just know this unit and co-unit of the adjunction. So essentially from this lemma we can find it derived, if you just check a lot of technical conditions that everything works fine, that if we have these natural transformations we can recover the map. That's what this lemma is saying. And the proof is of course completely elementary, just a simple computation. So you try to compute, for example, g bar, right? Simple computation based on these two formulas that represent neutrality conditions of the phi. So g bar, of course I can compute this as a composition with the identity on the f of x, right? Clearly this doesn't change the computation, but now in this form, using the, so I think this is the first formula, using the first formula, you can say that this is g of g, composition is eta sub x, right? Up to notation, this is the first formula. But that's exactly what we need. And for the second formula, the proof is more or less the same. Trying to understand f bar, rewrite this as a bar of the 1 on the g of x. The composition is f. You use the second formula. This is epsilon sub y. Sorry, this is not x, this is y. G of y. Composition, the functor f applied to the little f. So that's the whole proof. Now, let me formulate the theorem. So theorem, and another equivalent definition of what is adjunction between two functors. So again, I assume that I have this diagram, functor f from category C to the category D, and functor g going into the other direction. So there is a one-to-one correspondence between the following two types of data. So in the A, this is just the adjunction between functors f and g, meaning that we have this map phi, which is satisfying these two identities. And the second data, B, are natural transformations, the unit and co-unit of the adjunction. So natural transformation eta, so from the identity functor to the gf, and co-unit of the adjunction epsilon. So in this part B, these two functors satisfy triangle identity, these two natural transformations. So satisfying triangular identities. Okay, proof. Well, if we want to go from A to B, then we don't really need to prove anything, right? This is already done. We know that if we have a junction, we can define this natural transformation, and we proved the last thing we proved a week ago, that they satisfy the triangle identities. So clearly, A implies B. So that was done before. So essentially, the proof is how we can go from B to A. Okay, so let me write this. So we're going from B to A. Well, the first key observation I already told you is this lemma, right? If we have this information, we have these maps satisfying triangle identities, we can just define G bar and F bar using these formulas. So let me write this. So say by definition, G bar is what we have here. G of G, composition is the eta sub x. So with the same condition that G is any element in the df of x bar. So we just say that this is definitions. And F bar okay, so these are the definitions, and I want to separate this proof now into several steps. So the first step is the following claim. So I claim is that these maps that I just defined, that sends G to the G bar, and the second map that sends F to the F bar, are mutually inverse, right? Which we definitely need to prove this if you want to say that phi is a bijection. Okay, so the proof for F and for G is more or less the same. And for example, let's start with the G. And the proof is based on the looking at the following diagram. F. So this there is a piece of this diagram coming from the triangle identity. I'm just rewriting this triangle identity right now. Well, the only difference from this formula is that I plug in argument object x in this diagram, but it's the same diagram. Right? And then the second part of the diagram is the condition that I have a natural transformation, which is in this case epsilon. Okay. So that's something we already know. And now let's do some computation. So let's say that I want to compute G, right? And I can compute G from this diagram. For example, I can look at this composition, which is the identity, and then G, which is give me just G. Or I can go using the a little bit longer way, using this map, this map, and this map. So let me write this. So G is the composition. Yeah. Just need to do this in the right order. So the last map is the epsilon sub y, and then I have G is Fg. Yes, Fg. Fg and F eta of x. Well, it's simple computation, sorry that I take so many minutes to check the computation. Yeah, so this is correct. Now, of course, f is a functor, so we can rewrite this, keep epsilon sub y, composition f, and this is now applied to the g of the g, composition with the eta sub x, right, using that f as a functor. And this we can rewrite as the epsilon sub y composition with the f, which I apply by definition to the g bar, right? But now this is again definition for the g bar. So what we have here is g with the bar and then with the bar. So it means that if I apply this bar twice, I'll get the same thing. So kind of we have phi and phi inverse, and composition one direction is the identity. And the similar thing we can do if we look at the composition in the other order, or maybe I just try to fit this diagram here. We can look at the diagram with the g, f of x. So this is g, f of little f. Okay, so it's the same idea. This commutative square is the condition that we have a natural transformation, and this little triangle is the second triangle identity. And now do the same computation. I can write f as the composition of the g of the epsilon sub y. So take composition with the gf of f, and last map is a eta sub x. So again, g is a functor. We can rewrite this as the g that I apply to the composition of the epsilon sub y composing with the f of the little f. Take composition with the eta sub x. So this is g of the f bar composition with the eta sub x, which is f bar bar. So, and with this computation I claim that this proof that of the first observation is complete. These are indeed maps that are inverse to each other. Okay, so next step that we need to check is the neutrality conditions. Right? So I started with this data that I have on the B, which is two natural transformations, two triangle identities. I'm trying to recover the original data, namely the map phi. I've done this, but I need to be sure that this map phi is satisfying neutrality conditions, which are just two formulas. So let's do the computation. I need to look at the composition of the G, H and G with the bar. Now, using my definition, I can rewrite this as the G of the composition H and the little g composition with the eta sub x. This is the definition of the bar in this direction. But now, again, I use the fact that g is a functor, write this as the g of h, take composition with the g of the little g, composition with the eta sub x. Now let's look at the last two terms, g of the little g, composition with the eta sub x, which is g bar. So here, this thing is the g of h, composition with the g bar. And that's the end of the computation, right? Because this is exactly one of the two neutrality conditions. So we can recover neutrality conditions using those two definitions. And the same works for the second neutrality condition. Take composition of the F and H with the bar. Use the definition, epsilon sub y composition with the F of the FH. Use that this is a functor and get the same conclusion. I'm skipping a step, but this is the same step as before. So which is the second neutrality condition? Okay, so we get an adjunction between F and G. So essentially we started with the data in B and we produced data in A. And moreover, we can even check that the unit and co-unit of this new adjunction is precisely the same as we given here in the data in B. So unit of this adjunction, which is by definition 1 sub f of x with the bar, which using my definition I can compute as the g of the 1 sub f of x composing with the eta sub x, which is clearly, since this is still the identity transformation, the same thing as the eta sub x. And co-unit we can obtain by the same well, more or less the same computation. At least the idea is exactly the same. So we recovered from the data in B data in A, and we also can be completely sure that the unit and co-unit of these adjunctions of this new adjunction is precisely the same as the given in the B. So with this I can finish the proof of this theorem. Okay. So any questions? So this is the second way to think about the adjoint functors. And there is the one more way to think about this. But before we do this, I want to prove kind of separate proposition. I can prove it in any moment, so let's do it right now. It's a very natural question. So if you have a functor, and for example, you know that you have a, say, right adjoint, is it true that this right adjoint is unique? So of course, we expect this is unique, but this requires some little proof, so let's do this. So proposition. So if a functor f from category C to the category D admits right adjoint, and notice this is indeed a condition. I don't say that any functor, for example, always admits the right adjoint. It's kind of very special situation, or for the left adjoint. There are, I know only very few examples where you have a functor and this functor admits both left and right adjoint. Usually it's only one, and again there is no guarantee that even one exists. Okay, so suppose that we have a right adjoint. So then this adjoint is unique up to unique isomorphism. And moreover, functor f admits a right adjoint if and only if the following functor, take D, first argument is f with a blank, the second argument is some object y, so we can think about this as a functor from the C op to the category of sets. So this functor is representable for any object y in the category D. So admitting a right adjoint is kind of related to the condition, so some other functor which is constructed from this functor is representable. So first of all, is it clear what I mean by this notation? And so this home functor is naturally a bifunctor, right? Now if I fix the second argument, this will be a functor in the first argument, but now I just take the composition of this home functor in the first argument and the given functor f. So the composition of functors is a functor, and this is standard notation for this. Yeah, and clearly this is contravariant because f is covariant, but the home in the first argument is contravariant. So together the composition is contravariant. Okay. So in the proof of this statement, I think the proof is kind of easy and boring, so I'm going to skip some details. Essentially, I'm going to show you the main idea. So the main idea is that you can, for example, consider, of course there are different proofs for this, but the proof I'm going to do has the following main idea. So I introduce functor f with a lower star, which is the functor from the category D to the category of the contravariant functors on the C to the category of sets. So here f with a lower star on an object, right? So if I claim that I need such functor, I'm supposed to take an object in the category D, right? Plug in this object into f lower star and get a functor, contravariant functor on C that takes values in the sets. So by definition, this will be D f blank y, right? Clearly, this is a functor. It's very easy to check. Okay, but if I know, for example, that f has a right adjoint, I can also rewrite this in equivalent way as the C blank g of y for the right adjoint of the f. So here, g is right adjoint for the f. Okay. Now, let's look at the diagram. So we have category D, we have functor f with a lower star, the category of functors. Well, it's also kind of by trivial conditions. If you, well, okay, not trivial, by trivial reasons. So if these are two composition of functors, right? But now, if you have, for example, some map, say, let's call this f from the y to the y bar, right? You're taking just composition of two functors. So you already know how the f is acting on this little f, and you know how the home in the first argument is also acting. So this is you just compose these two things. Okay. Now, what we can notice with this, when you have a right adjoint, this is exactly condition of the proposition, then you can rewrite your functor in this way. But this is what this formula is telling you. It's telling you that actually this is a functor from the C op to the sets of a very special form. This is a presentable functor. So In fact, I can also write category C here, right? So here there is the Yoneda embedding that we discussed last time, so H with the blank, right? And in fact, we can use now, when we're proving the theorem that the being an equivalence of categories is the same thing as being essential, surjective, and fully faithful, we prove the lemma that if this is true for objects, this is true for functors. So if the image of functor is in some subcategory, then in fact there is a functor such that we have such decomposition. So let's call this functor G0. Okay? So this factorization of the f with the lower star follows from the lemma that I proved, I don't know, 2 weeks ago, before I proved the essential surjective plus fully faithful is the same as equivalence. So I can apply this lemma again here.
So this standard line is what category that have an object isomorphic to any object?
Sorry, can you repeat the question?
Ну, мы можем вот все подчеркнуто это из какой темы получается у нас категория?
This is from the lemma. So there was the.
Ну, там lemma, да, была.
I think this is the first statement in this course that I actually proved. So this is the lemma. Yeah, so I can claim that there is the unique such functor G0 from the category D to the category C. And since I have this factorization, well, it means that f lower star is the same as the Ioannidis embedding composition with the G0. But what it means to have such formula, it means precisely that the df blank comma y is isomorphic to the C blank G0 of y. These two formulas are precisely the same. I just rewrite this formula, right? So if you apply G0 to the object y, but then you're supposed to have to take functor, which is Ioannidis functor, where the second argument is just this argument. So you can see that if you have a right adjoint, then you can construct for any right adjoint this right adjoint G0, which also works as a right adjoint. But now I claim that actually G is isomorphic to the G0. Do you see how I can conclude that from this formula and maybe also that formula, I can claim that the two functors are the same? Well, let's start with a simple thing. Okay, do you see why g of y for g0 of y for any y is the same as the g of y?
Because of the transitivity of the equivalence,
No, I don't think so. This is because of the Ioannidis lemma, right? This is a representable functor, and this is a representable functor, and they coincide. Well, since they just this functor. And the two representable functors coincide, it means that this object is isomorphic to this object in the canonical way. But I'm leaving as an exercise that you have only just isomorphism in objects, you can also do this for the arrows, essentially because everything is functorial, is constructed by some other functors. So this is by Ioannidis lemma. Okay. Now to work with the third way of describing adjunctions between two functors, I need to introduce the notion, quite elementary notion actually, of the initial and terminal objects. So definition with several parts. So first, an object, I'm going to call this T for terminal, so this is object in some category C, so it's called terminal if for any other object x in this category there is a unique map f from the x to the t. So for the terminal objects there is only one map from any other object. So part 2 is just the opposite version of this. An object S in the category C is called initial if now for any object X in this category there is a unique map F from the initial object S to the object X. Okay, just for completeness, I'm going to introduce two more parts of this definition. We're going to use them later. So Z in the category C is called zero object if it is initial and final at the same time. And finally, yeah. So terminal, let me add this in the definition, or also final. Yeah, thank you. And finally, part 4 of this definition, if we have a map from y to x, this is a zero map. If I can find the factorization of this map x, z, y, such that this object z, so I can take map f, factor this as the composition of two other maps with the object z in the middle, and this object z in the middle is the zero object. So, where z is a zero object. So in any category, if it exists, you can. Yeah. So it's a very natural definition. You want to call a map a zero map if you can factor this map through a zero object. Note that this makes sense in any category, if of course if zero object exists. But usually we're going to talk about the zero objects and zero maps in the abelian categories a little bit later. Okay, so that's the definition, but before we proceed, I want to look at several elementary examples. So let's start with the simplest possible example, the category of sets. Can you tell me, okay, let's do the example. So in the category of sets, can you tell me, do we have an initial object, do we have a final object? And what are those objects, if they exist? Again, it's not necessarily true that in any category you have those objects. It's just an existence of such two objects is an additional requirement. Yeah, so initial S, right? So S, I'm going to call this S. This is an empty set, right? Because I think it's clear. I don't need to explain this. How about the terminal object? Okay, I like this answer. So, but why the answer is just a singleton? No, there was.
So it's clear that from from singleton they have. Ну там
Yeah.
единственное.
So there is just you take any set and there is only one map that takes any element in the set and sends this to this star. So there are no other options. And by the way, here you can notice one interesting thing. It doesn't matter which singleton you take. Right. So it means that in this case, the terminal object, but in general also initial object, they are not unique. They only unique up to isomorphism. So there are plenty of singletons, but they all isomorphic as a sets, meaning that there is a bijection between them. Okay. So the second example, we can take the category of monoids or the category of groups. The answer is the same. So how about initial and final objects in this, or terminal objects in this category? And is it initial or final?
I think same answer.
Yeah, so in this case there is a zero object, and the zero object is precisely this trivial group with only one element, which is the identity element. Well, maybe let's look at the algebraic example. So let's take left R modules. What are the initial and final objects? Yep, the same. We have a zero object, which is just a zero module, which at least tells you that for modules this is a reasonable notion. That's what you expect to be a zero object, right? Maybe a little bit more interesting if you look at the category of rings. So let's start with the initial object. So what is S? Mm-hmm. And why? We assume that rings have the identity elements. So then this map is just the canonical map where you take one in the Z and send this to the identity in the ring, and then everything is defined. Okay. How about?
So rings with unity, yes.
Yeah. So all my rings always have the multiplicative identity. So this is the initial object, and how about the final or terminal? But what's the zero ring? It has only.
He has no unity, I think.
Yeah.
У нас единица одна или нет?
Well, and so you can see now the answer actually depends how you specify this category. For example, you can consider two different versions. In one version, you include zero ring as an object in this category, and in the other version, there is no zero ring. So this is up to you. So we can say that this is zero ring if we have such object in the category of rings. And for example, if you take a category without zero ring, right, you always assume that in any object in your category, zero is not the same as one, which is usually people do in algebra, right? Usually rings are not zero rings. Then in this category, there is no terminal object. Okay, maybe one more example. How about fields? So in the category fields, in this case, no initial object. Yeah.
То можно сказать, что тут симорфизм вложения более вложенного во все.
That also works. Yeah, and indeed that was correct character mark. You can consider subcategory fields with the index p, fields of the characteristic p. Then you have initial objects. If p is equal to 0, this is q. If p is some prime, this is fp. But for the terminal object, the situation is more or less the same as for the rings. If you have a 0 field in this category, then this is the terminal object. If you don't have a 0 field, then there is no. So here is everything is the same. Okay, maybe I start with examples for a moment. Well, you might get an impression that this is kind of a silly notion, this initial terminal objects, right? Because we can easily compute what it is if we given some category that we know. But the idea of this initial and terminal objects is a little bit different. You start with a category and maybe a pair of categories, and then you construct another more interesting category, and you study initial or terminal objects in this additional new category. And that's what happens for the first time in the next description of the adjoint functors. So we're going to study initial objects. So let me check this. Yeah, initial objects in one of the comma categories. And to do this, I need to introduce the notion of a comma category. So another definition. Yeah, but before I go do this, I forget one thing. This is silly, but still exercise. Initial or final object is unique up to unique isomorphism. Of course, if it exists. Okay, so now the definition of a comma category. So in this definition, I assume that I have three categories and two functors. So let me call this categories C, D, and E. So functors will be F and G. So, and the category E is in the center, C is on the left, D is on the right. And the functors are functors, so F is from C to the E and G is from D to the E. So this is we assume that we're given such diagram. So the comma category notation is F with the down arrow G, has triples C, H, D. So where C is an object in the category C, D is of course object in the category D, and H is a map in the category E from the F of C to the G of D. So these are the objects. And the maps from one triple FHD to another triple, sorry, CHD to another triple C prime, H prime, D prime. Well, this is just two maps. So F that lives in the C between C and C prime. G is a map in the category D from D to D prime, such that the following square is commutative. We have F of C. Well, maybe before we do this, and they have G of D, and there is map H. So notice that this diagram is precisely the object in this comma category. Right? We have object C. Well, I just want to say that if you just look at this definition, you have object C, you have object D, and you also have a map H, which is map like this. So the objects are such diagrams, and the maps are pairs of maps, such that if you draw the following square, then the square is commutative. So that's the definition of a comma category. It's kind of a general definition, and really in this course we don't really need this general definition of a comma category in the situation where I have 3 categories and 2 functors. But this general definition has a lot of special versions. So essentially the only reason I'm just telling you this general definition so that you can see that the special versions are special cases of one more general definition. But what we need is the following, I think, 4 special cases. And these are examples that we're going to use several times in this course. So first of all, there is a slice category. So this is the following case. We fix an object C in the category. And now, instead of this general diagram, these 2 functors and 3 categories, we consider this diagram. We have C, the identity functor from C to C. And then there is a functor from a category with 1 object, which is kind of induced by this object C. So here, there's categories where we have only 1 object and only 1 arrow, and we're sending this object to the object C, which we fix in the category C. And the identity here is sent to the identity. So this is just not the explanation of the notation C with a low star. So notation in this case, we have identity on the category C, comma category with the functor C bar, but usually people don't write something like this. Yeah, well, the shorter way to write this is just instead of the identity for the functor, write the category, and instead of this C lower star, just write object C, or another even more common notation is the C over C, meaning that here we kind of study objects in the category C over this fixed object C. Well, if you just look at this diagram and plug in this special diagram into the definition, you'll see that the objects are pairs where you have x, and h. So x is an object in the category C, and h is a map from the x to the C. And the maps in this situation are the following. You have x, h to the C, x prime, h prime to the C, and then the map is just a map from x to the x prime such that this triangle is commutative. So indeed you can see this is a special case, and you probably already know some examples of such slice categories. So can you give me an example? Well, maybe not really. Maybe what you know already, maybe I can postpone this question. There is a notion of a co-slice category. So you definitely know examples of co-slice categories. So 2 co-slice category, which kind of need to consider dual situation where instead of considering objects with the maps to the given object, you consider objects with the map from the given object. So let me just do this briefly. I have identity category C lower star C, and then identity functor from C to C. So in this case, notation would be well, it's kind of the same as before, but it's like left to right classes, the same difference. So, and the examples of co-slice categories that you probably know is the following. You can consider pointed category of sets, right? So objects are sets. Object here is a set with a distinguished point, and the map is supposed to preserve this distinguished point. So in this case, you can write this as a co-slice category. So this is one example. And another example of a co-slice category is the category, say, of commutative algebras over a given ring. Right, so in this case, this is the same thing as the co-slice category for the ring R and the category of commutative rings. Okay? So in this situation you're supposed to have opposite map, so C to the X. So clearly if C is just a singleton, then such diagram is precisely the same thing as a set with a distinguished point. And the same is here. If the object C is just a fixed commutative ring R, then such diagram is precisely what we call a commutative algebra over R. Okay, so these are slice and co-slice categories. There are other special cases. So for example, sometimes it is useful to take the arrow category So in this case, the diagram is just 3 copies of the same category and 2 identity functors. So you'll get the category of arrows of the category C, which is by definition the following comma category. Right, so clearly in this case the objects are just arrows, meaning that you have something like x, f, y, and the map between 2 arrows is just the following commutative diagram. So, and finally, special case number 4 is the following. You have category with one object. Again, fix an object C, take the functor C lower star, and the second functor, well, is just some functor, so it's a little bit more general situation. So in this case, C star G, we can use notation, shorter notation. Instead of writing functor C, we can just write the corresponding object C. Okay, so let me write that objects are pairs, D and H, so such that D in this case is an object in the D, and F is a map from C, sorry, not F, H. H is a map from C to the G of T. So essentially the objects are diagrams of this form, and the maps are just special case of maps that we have before. So this last kind of example will be important for what we do with the joint functors. So the map from the dh to the d prime h prime, if I call this G, then this is a map from the D to the D prime between objects such that I have the following commutative triangle. So C, H prime, G of G, so I'll leave it to you to check that this is a special case of the diagram if the first functor is just C lower star. Okay. So let's look at the example. Oh, this last category. So what are terminal objects in SU? So what are SU in this situation? I have identity category. S is just a set. So I have the corresponding functor S lower star, which takes this unique object here to this given set S in the category of sets. And the functor U is the forgetful functor from the category of groups. So this is the diagram, and I'm asking you to find the terminal objects in this situation. So let's introduce notation. So let's say that the terminal object T, in this case, so that this is supposed to be a pair, so let's call this pair G sub T for terminal and H sub T. So what is it? If you solve this exercise, you will see why this theory of common categories is relevant when we study adjoint functors. Well, I'm not sure that this is a correct question. I'm not sure whether I need to consider terminal or initial. So let's do the computation together. So we have set S. So what are maps, right? So there is map H sub T to the U of the G sub T, and say there is some other map to the U of G, right? So if I can say that there is a unique map F as a map of groups from the G sub T to the G, right? So then I can write here U of F. Yes, so but sorry, this is terminal. If I want this to be terminal, then so the map is in the other direction. Yes. Right? So for any other group and such map, so you take any group and suppose you have a map of sets, so you can map this set S to the group, but you forget that this is a group and just consider this as a set, right? Any such map, you can for any such map, you can find a map F such that this arrow here is unique. Right? Yes, so this is also T is in the wrong position. T is supposed to be here. Yeah, it looks like this makes some more sense if I try to understand the initial object. Right, because if I have the initial object, let's do this with the initial object. So this is why I wasn't sure. So let's write this S everywhere S. So this is S, and now the arrow is in the other direction. So now we can see that, again, whenever I have a map of the set to this group G, I can uniquely extend this as a map of groups from the GS to the G, right? And when we can do this unique extension from the set to some group GS. Well, this is precisely the definition of a free group. So in this case, GS is the free group on the set S. Right? But you can easily check that the construction of a free group is the left adjoint to the forgetful functor U. Какое? That's clear. If you just look at what happens, well, you have a set, right? Whenever you have a map from this set to the group, you can uniquely construct a map of groups from the GS to G, such that you have this commutative diagram. But that precisely means that GS is a free group generated by the set S, by definition of a free group on the set S. Yeah, sorry, so it looks like in the correct example this has to be an initial object, not the terminal object. Sorry for that. But this, at least why we consider this example, the idea is that you can see a relation that somehow such diagrams where you have object and some functor, and you study initial objects in such comma categories, they are related to the existence, in this case, of the left adjoint. So is that even? Yeah, okay. Да. И это в точности будет условие 3, которые эквивалентны определению. Okay, so before I do this, I need a definition and a lemma. So the definition, a universal arrow, well, it's in fact just an object in the comma category, so it's pair D and H, where H is a map from C to the G of D. So you can say that this is universal arrow, say, for the functor G. So is an initial object in the comma category C arrow G. So lemma so suppose we have two functors, so f from C to D, G functor in the other direction, and f is left adjoint to the G. So then f of C, eta sub C, is universal arrow in the comma category C, G. And that is true for any object C in the category C. So essentially this is a way, third way to look at the definition of an adjoint pair. So you can go from the adjoint pair to this data, and this data is the universal arrow in this comma category. So the logic is as before. Before we proved the lemma that from the adjunction we can derive two natural transformations satisfying triangle identities. So here we derive this data, and then there will be a theorem that from this data you can derive back the adjunction between f and g. So, but this is probably something that we're going to do next time. But today we're going to prove this lemma. In the definition of the universal arrow? Well, it's quite straightforward definition in the sense that you consider the comma category precisely what was in the special case 4. And then you just say that the initial object in this comma category is called by definition a universal arrow for this functor G. So proof. So for any pair D and H, which is an object in the comma category C and G, again, this simply means that the, let me add this in parentheses, D is an object in the category D, and H is a map in the category C from the object C to the G of D. So take an object in the comma category, right? But since this H lives in this home space for the category C, we can say that there is unique H bar which exists by the adjunction. So this is in the D underlined from the F of C to the D, right? And the following triangle is commutative. So we have C, eta sub C, GF of C, G of the H bar, G of D, H. Okay, so why the triangle is commutative?
So it's by natural condition.
Yeah, this is precisely one of the two formulas that we use all the time. I just wrote instead of formula this commutative square. So, but this, okay, so we know that the square is commutative by what we know about the naturality of the map phi, but from the point of view of these universal arrows, what it means that this triangle is commutative. Here, we start with any object, right? An object, essentially kind of this diagram, CH that maps to the G of D, right? So that's an object in the comma category. It's at least a natural graphical way to represent this object. And now we see that for any such object, we constructed a unique map from this object to the given object. So that's precisely the definition of the initial object, but in this comma category. So this diagram is the initial object in the category. So F, just give me a second to finish the sentence. So is an initial object in the comma category C arrow G. And that's the end of the proof. Okay, so what was the question?
Why this map is unique?
Well, this map is unique. Well, this map is given by the H bar, right? But the H bar is unique because it's uniquely determined by the map H. Again, commutativity we discussed before. It is, remember that we wrote two formulas for the naturality. This is just one of those formulas. Special case of that formula. Okay, so it looks like I'm again in the situation as before. I proved something before a big theorem, but I don't have time to prove this theorem, so let's take a break and I prove this big theorem next time.
Почему существует все-таки для полей начальный ответ? Почему для полей не существует начальный ответ?
Ну, это был бы такой объект, который